Hi, this is Professor Fernandez, and this is video 1 in lesson 10. We'll be talking here about the rules of differentiation. So I'm going to go through 2 examples from Calculus Simplified to help you get comfortable with that topic. So what do we mean by the rules of differentiation? Well, up to this point in this video series, also in this course, we have been thinking about differentiation in terms of the limit definition of the derivative, which is a very I would call it an intuitive way of coming up with the notion of the derivative. If you go back and read through the sections of the textbook here in terms of how this came about, and also think about the geometry, and then just watch some of the videos and me explaining it. However, it is not a useful computational tool. Calculating limits of this difference quotient can get very, very complicated for even the simplest functions like f of x equals x cubed. If you take a look at some of the previous videos, like video 8.2, doing those calculations take a while. So we have always longed for a faster and easier way to calculate limits. This is the first time that we are going to meet those faster techniques. So we're going to start talking here about rules of differentiation, and we will meet several rules over the next few videos. The simplest rules we alluded to in the previous video, video 9. I want to say, let me double check here, video 9.3. So if you look at video 9.3, there we were calculating f prime of x using the limit definition, and I kind of alluded to some rules that will be coming up and make our lives easier. This is that video. All right, so enough of that. What are the rules? Let's start with the simplest rules. Okay, so these are the sum, difference, and constant multiple rules. Suppose f and g are differentiable functions. Remember, differentiability here is important, so we talked about that in video 9.1. So if you want to review differentiability, what that means, hop over there. And c is a real number. Then, these 3 rules. What do they say? If I have a sum of 2 differentiable functions, then the derivative is the sum of their derivatives. So said more succinctly, the derivative of a sum is the sum of the derivatives. Great. Similar thing is true for difference. The derivative of a difference of 2 differentiable functions is the difference of the derivatives. And constant multiple, the derivative of a multiple of a differentiable function is the multiple of that derivative. So you can say these out in English, and it's easier to remember them that way. Or, if it makes better sense to write them out like I did over here, that makes sense. Long story short, another way to remember this that's a bit more visual and I always like is that, again, we're using prime here as the derivative operator. Notice what happened to the prime. Here it was outside the parentheses, and here it got distributed to both the f and the g. Same thing here with the prime, gets distributed to both the f and the g. And the prime here doesn't really get distributed to the f and the c, right? So this one is a little different in terms of that rule. This is why I explained this distribution visual way last. Don't want to confuse anyone. But it is helpful to remember that in case it comes in handy. Okay, so let's use these properties over here in our first example, differentiate this function. Again, we could do this using the limit definition of the derivative. Don't want to do that, right? Been there, done that. Takes too long, although this is a linear function, so it wouldn't take as long. But let's use the derivative rules. So the derivative of 3x plus 5 would be 3x plus 5 prime derivative. Notice that this is a sum of 2 functions, so I can use my sum rule. The derivative of a sum is the sum, the sum of the derivatives. Great. And now I have to think about what each one of these is. Again, I could use a limit definition, or I could just bring in everything we've learned so far about derivatives. 3x is a linear function. Its graph looks kind of like that. Okay? And if I want to find its derivative, at every point, remember what the derivative is, it's the slope of the tangent line. Pick another point here, draw a tangent line, find its slope. Pick a point here, draw a tangent line, find its slope. You can see that the slope of these green lines is the same as the slope of the blue line. In other words, the derivative of 3x is going to be 3 because the slope of the blue line is 3. It's a linear function with slope 3. So we know the answer here, 3. Isn't that nice? We didn't have to do any limit derivative definition of the derivative calculations or any of that. We just used the geometric interpretation of the derivative. Great. Let's do it again. So how about 5? I'm going to go back here and draw my function y equals 5. There it is. Pick any point on the graph, draw a tangent line. Pick any point, draw a tangent line. Pick any point, draw a tangent line. You can see that all the tangent lines are horizontal, right? Just like the graph. Again, y equals 5 is a linear function. It's a very special type of linear function. It's 5 plus 0x, has slope 0. So for all the same reasons we just talked about, the derivative of y equals 5 is the slope of the line y equals 5, which is 0. So the derivative here is 0. Long story short, conclusion, the derivative of 3x plus 5 is 3. Should make sense because this is a line with slope 3, and everything we just talked about tells us that the derivative is the same as the slope of the line for a linear function. Okay, so really this is the part that I wanted to illustrate here, right? So that's the first application of the first derivative rule. Notice what the rule did for us. It took the problem of differentiating a function that is the sum of other functions, and it broken down into the sum of the derivatives of those other functions. So think of these 3 rules over here as kind of like slice and dice type rules. You know, you have a big function, the sum of a bunch of other functions. These rules help you to express the derivative of that big function in terms of the derivatives of the constituent parts. Okay, last example here. Differentiate g of x equals mx plus b. So this is again a linear function. This is, you know, the general form of a linear function that is not a vertical line like x equals 7 or something. And we don't know what m and b are. They are parameters, but we do know what they mean. This is the slope. This is the y value of the y-intercept. Okay, how do we differentiate this? Well, we could do things all over again, by which I mean everything we did up here we could do, or we could just remember what just happened. This is a line. I don't know its slope. It might look like this, it might look like that, it might look like this, I don't know. But I do know that m is the parameter that represents its slope. And I know that because whatever the line looks like, if I draw tangent lines, the slope of the tangent line is the slope of the line, I kind of know what the answer is going to be, right? I know the answer is going to be g prime of x equals m. Okay, so again, the same slope as the slope of the line. So we kind of know the answer, and we could stop there, but that doesn't really help us apply any one of these rules. So I'm going to give you another way that actually illustrates the rules and applies them. It's not very different from what we just did, right? I'm differentiating mx plus b, noticing again that this is the sum of 2 functions, mx, linear function with 0 y-intercept, and y equals b, which is a constant function. So therefore, each of these I can differentiate and then add the results. So the derivative of mx, like we talked about before, linear function, slope m, it's just m. The derivative of b is a number, y equals b is a horizontal line. The tangent lines are horizontal, slope 0. So g prime of x, therefore, is just m, which gives us the same answer as before. Okay, last thing I want to talk about really quickly, I am using a theorem, right? So it is always good to check the hypotheses of a theorem before you invoke its conclusions. The only hypotheses in this theorem were that f and g were differentiable functions. You know, we didn't end up using number 3 necessarily. We could talk about how to use that over here. Maybe I'll do that in a minute. But the point is that we need to know that f and g are differentiable functions to begin with. I didn't really emphasize that for this example because we're dealing with lines, okay? mx plus b and 3x plus 5. We know that those are differentiable functions, right? For all the reasons we talked about graphically over here, but also because if you write down the limit definition, the limits are just, that you calculate in the end, are just limits of numbers, like the limit of 3 or the limit of 5 or something like that. Okay, so what did I want to talk about with the constant multiple? So let's see how, even another way to put in some of the intermediate steps over here to show you how you could make use of that constant multiple rule to illustrate that one. So this was the derivative of a horizontal line, y equals b, so that's 0. Over here, we can now view this as m, which is a number, times x, the function. So I could use the constant multiple rule. So I could say this is equal to m times the derivative of x. See? So in other words, mx prime is m derivative of x. To use a numerical example, 3x prime is 3 derivative of x. So again, we've made things a little simpler. If I graph the function 3x, it's 3 times as sloped, if you will, as the function x. The point is that the function y equals x, I can find the slope of the tangent lines for a little bit easier than the function 3x. It's the same thing though. The slopes of the tangent lines are the same as the slope of the line, which is 1. So x prime is 1. So this would give me 3 times 1, which is just 3. Same idea up here. X prime is 1, so this would give me m times 1, which is m. So long story short, we get the same answer as before. G prime of x is m. We've now done it, 3 different ways, right? 1 over here with graphical, 2 over here, not using the constant multiple rule, putting in some graphical reasoning for this part over here. And then 3, what we just did over here, using all of the rules. The sum rule, constant multiple rule over here, and then just thinking about what the derivative of x is. Great, so the only thing I would mention for this, again, this is a theorem down here, so you want to know and make sure that the functions are differentiable. We talked about differentiable in the video 8.2. So make sure that you have some sense of 9.1 is where we talked about differentiability. So make sure you have some sense of differentiability before you start invoking these rules. If you don't, and you just use them, you might end up with a conclusion that is not supported by the reality of the situation because one of the functions may not be differentiable somewhere. Okay, thanks for watching.